Okay, students, we'll start by looking at the topic of binomial distribution. In the topic of binomial distribution, we'll first look at what is a random variable. All right? A random variable is actually a variable that can take on different numerical values according to the results of the experiment. We usually represent random variables by capital letters such as X, Y, or A, B, C, and so on. Okay, but the main thing is that they must be represented by capital letters. And the possible values that a random variable can take on are represented by lowercase letters x, y, and so on. So for example, the random variable x can take on the value small x. Okay, so an example would be random variable x can take on the value 3. Okay, so now let's consider the experiment when a fair coin is tossed twice, 2 times. So we know that the sample space, which is made up of all the possible outcomes of this experiment, will be head head, head tail, tail head, or tail tail. Okay, so if we let x, which is a random variable representing or denoting the number of hits obtained, so x represents number of hits obtained when a fair coin is tossed twice. So we notice that we'll observe that the possible values of x will be 0, 1, or 2. So we can obtain 0 head, that means no head, that means both tosses are tail, or 1 head, so it can be head tail or tail head, or we can obtain 2 heads, that means the outcome will be head head. Alright, so these are the possible values that a random variable can take on. 0, 1, 2 are numerical values. And the value that a random variable obtained in this experiment is subjected to chance. So that's why, so it's random. Alright, so that's why we have this name. X is a random variable. Random because it's subjected to chance, and variable because the values can vary. So in this example, x can take on 0, 1, or 2. Okay, so I've already explained x random variable take on the value 1. What does it mean? It means it's the event of obtaining 1 head when the fair coin is tossed 2 times. So probability x equals to 1 is the probability of obtaining 1 head when you toss a fair coin 2 times. So probability x equals to 1, we have learned in the previous topic in probability that it is equals to probability head tail plus probability tail head. So you sub in the respective probability and add out the 2 possible cases, and you will get your answer for probability x equals to 1 as half. That means the probability of obtaining 1 head when you toss a fair coin twice is half. Okay, after knowing what is a random variable can be classified into 2 types. It can either be a discrete random variable or it can be a continuous random variable. So for the purpose of H1 Maths syllabus, you will need to know what is a discrete random variable. Okay, so a discrete random variable can only take on a finite or countably infinite number of values. What does it mean by these two terms? What does it mean for finite number of values? That means you can think of it as limited number of values. So a discrete random variable can only take on a limited number of values. That means you can actually count how many values in total that the discrete random variable can take on. Okay, and a discrete random variable, it can only take on, so the values that it take on must be, so the values that a discrete random variable take on must be natural numbers or whole numbers. Okay, so a discrete random variable, other than taking a finite number of values, it can also take on countably infinite number of values. What does it mean? That means infinite number of values means you can't count it, but then you can, as in there's no limit to the number of values they can take on, but you can actually count them one by one. All right, so in the sense that they are natural numbers, so you can still count. All right, to concretize what I've just meant, let's look at three examples of discrete random variable. The first example, if you have a fair coin and you toss it 4 times, so you define x as a random variable, number of heads obtained in tossing a fair coin 4 times. So x is a discrete random variable because x can only take on natural numbers. Okay, so 0, 1, 2, 3, or 4. So we can either have 0 head obtained, or 1 head obtained, or 2 heads obtained, or 3 heads obtained, or 4 heads obtained. All right, so therefore, it can take on a finite number of values. Okay, and they are all natural numbers. Example 2, let x be number of eggs that a hen lays in a day. So this is also a discrete random variable because the possible values will be 0, 1, 2, and so on. So a hen can lay 0 egg in a day, or 1 egg, or 2 eggs, or 3 eggs, or 4 eggs, or even 100 eggs, 105 eggs, and so on. So although it's infinite number of values that the random variable x can take on, but you can actually count them in the sense that they are all natural numbers. So therefore, random variable x is classified as a discrete random variable. All right, let's look at example 3. Random variable y is defined as number of accidents reported on an expressway in a period of 4 hours, in a duration of 4 hours. So why random variable y is also a discrete random variable? Why is it so? Because we can have infinite number of accidents in 4 hours, but the values are countable. So we can have 0. So y, the values, possible values that random variable can take on can be 0, 1, 2, 3, 4, and so on. So in this case, so it is countably infinite number of values. Okay, so it could be infinite number of values, but then we can still count them in the sense that they are still natural numbers. So we can still count them 0, 1, or 2 accidents, or 3 accidents, or 4 accidents, or 5 accidents, and so on. So it's still countably infinite number of values. So therefore, random variable y is also a discrete random variable. Okay, so let's look at these two, the next page. Let's look at these two questions or these two scenarios. Which one do you think is a discrete random variable and why? Okay, scenario number 1. You have 4 cards and they're drawn from a pack of playing cards. That means from a set of 52 playing cards or poker cards. Let random variable x be defined as number of jacks obtained. Okay, so number of jacks obtained when 4 cards are drawn from a pack of playing cards. So is random variable x a discrete random variable? Yes, because random variable x can take values x equals to 0, 1, 2, 3, or 4. And all these are countable number of values. Okay, or finite number of values. So random variable x, it can be either 0, that means 0 jack obtained, or 1 jack obtained, or 2 jacks obtained, or 3 jacks obtained, or 4 jacks obtained. okay, when you draw 4 cards from a pack of playing cards. So 0, 1, 2, 3, 4, they are finite or countable number of values, and they are all natural numbers. Okay, let's look at scenario number 2. Let y be the random variable, the height of a randomly chosen 18-year-old student. So, what can we say about the height of a student? Is it a discrete random variable? No, it is not. Random variable y is not a discrete random variable. Reason being, random variable y can take any values in a given range. So, therefore, it is a non-countable number of values. All right. So, for example, the height. So it may not be natural numbers. Right. The height of a randomly chosen 18-year-old student, it may be 172.3 cm. So therefore, this is not a natural number or not a whole number, and therefore random variable y is not a discrete random variable. Okay, now that you know what is a random variable, as well as also what is a discrete random variable, let's move on to section 3.2. Section 3.2, all right, you have learned in the previous chapter how to calculate probability of an event in a given experiment. So let's consider this scenario. You have a biased coin, and this biased coin is tossed 3 times. All right, tossed 3 times. Probability of getting heads in each toss of the coin is 2/3. So calculate the probability of getting no heads, in other words, 0 head. In part 2, calculate probability of getting exactly 2 heads. Okay, so since the question say that probability of getting heads in each toss of coin is 2/3, therefore probability of getting tails. So because in each toss of the coin, you either get a head or a tail. So probability of getting tail will then be 1 minus 2/3, which is 1/3. So let's draw a tree diagram, right? For this to represent all the possible outcomes of this experiment. So there are 3 tosses of the coin. Okay, so therefore your tree diagram will have 3 stages. First toss, second toss, third toss. So probability of getting a head is 2/3 and probability of getting a tail is 1/3 in each toss of the coin, right? Regardless whether it's the first toss or second toss or third toss. So using this tree diagram, we can calculate probability in part 1. No heads is obtained. That means probability 3 TTT. All right, probability of getting tail. So that will be this part. 1/3 times 1/3 times 1/3. Okay. Part 2, probability of getting exactly 2 heads. Exactly 2 heads, we can have 3 cases. Either head, tail, or head, tail, or tail, head. All right, so head, tail will be this part. Head, tail, head will be this one. Tail, head will be this. So we just multiply all the 3 probability and sum up the 3 cases, we'll be able to get the answer, okay, which is 4/9. So this is what you have learned in chapter 2 on probability, right? Which is nothing new. So let's look at example 1. Example 1, based on the example in section 3.2 or the scenario given in section 3.2, we are asked to calculate what's the probability of getting no heads, exactly 1 head, exactly 2 heads, and all heads. So now that you know what is a random variable, so we will define x as the random variable, number of heads obtained when a biased coin is tossed 3 times. So what is the probability of getting? We'll calculate what's the probability of getting no heads, that means x is 0. 1 head means x is 1. 2 heads means x is 2. And all heads means 3 heads. So that means x is 3. So let's calculate the probability of each of the possible outcome. Alright, so we have already calculated part 1 and part 3 in the above on page 4. Alright, so we know that. Let's take a closer look at this one. Probability of getting in part 1, no heads, that means probability s equals to 0. So that means no heads means the outcome is probability of tail, tail, tail. So we know that it is 1/3 to the power of 3. Okay, so 1/3 to the power of 3. So what is this part here? This part here basically just means that, okay, the top, there are two numbers. The top number is the number of tosses of the coin. So the coin is tossed 3 times. So the top number is 3. And this bottom number actually represents number of heads, number of heads obtained. So in part 1, we are finding probability of x equals to 0. That means no heads obtained. So the bottom number is 0. Alright, this also means 3 choose 0. That means from 3 tosses of the coin, I want to choose 0. I want to choose or obtain 0 head. Alright, in part 1. So 3 choose 0. Alright, then this 1/3 to the power of 3 is just the same as this part here. Alright, 1/3 to the power of 3, which is obtained from the tree diagram. So you can use your GC. This part, 3 choose 0, is the same as this part. I can write it as NCR, right? Which is where N is 3 and R, this is N and this is your R. So you have learned how to calculate NCR in the chapter on permutation and combination. So we realize if you press a GC, 3 choose 0 is just one way, right? So that's how you obtain this. Okay, so it's the same answer as the above that we get from a tree diagram. Okay, part 2, probability x equals to 1 means obtaining one head. So to obtain one head, we can have 3 cases: head, tail, tail, or tail, head, tail, or tail, tail, head. Okay, so the same reasoning as part 1. From a total of 3 tosses of the coin, I want to obtain one head. So it's 3 choose 1. Okay, then what's the probability of obtaining one head? It will be 2/3. And what's the probability of obtaining 2 tails? So it will be probability of obtaining one tail is 1/3, and probability of obtaining the second tail will be another 1/3. So 1/3 times 1/3, or I can simplify it as 1/3 squared. So you just press a GC, you will get the answer 2/9. Alright, so again, just to remind you, this is 3 choose 1. Alright, if you can press your GC, the answer is 3. It has a value of 3. Alright, okay, now let's look at part 3. Probability s equals to 2 means obtaining 2 heads. So it can either be head, head, tail, or head, tail, head, or tail, head, head. Okay, we have already calculated this part over here in here. Okay, so obtaining 2, so out of 3 tosses of the coin, I want to obtain 2 heads. So it's 3 choose 2. Okay, then to obtain 2 heads, so probability of obtaining a head is 2/3. Then probability of obtaining a second head will be times 2/3 again. So it's 2/3 squared. Probability of obtaining a tail is 1/3. Okay, so therefore, that's how you get the answer 4/9. Okay, part 3. What's the probability of obtaining all heads? Means total of 3 heads. So it's probability head, head, head. Okay, so from a total of 3 tosses of a coin, I want to obtain 3 heads. So it's 3 choose 3. Probability of obtaining a head is 2/3. So 3 heads will be 2/3 times 2/3 times 2/3, or 2/3 to the power of 3. Okay, press a GC, you will get an answer 8/27. Okay, so now I want you to observe this table. these four values here, 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 and here. So we can generalize or deduce that probability x, capital X, or random variable x take on a particular value, small x, will be 3, will always be 3 choose x. So this value in the denominator will be this particular value of that the random variable take on at a point of time. Okay, so for example, let's look at this one. If we are looking at probability x equals to 2, so this 2 is our small x. Okay, so therefore over here is 3 choose 2 or 3 choose x. Multiply by 2/3 to the power of, okay, this 2 is again our x, and then multiply by 1/3 to the power of 1. 1 is the same as 3 minus x, where in part 3, our small x is 2. So 3 minus 2 gives you the power 1. Alright, so we generalize by observing the expression for part 1, part 2, part 3, and part 4. So we are able to come up with this expression or this formula. Alright, over here, where small x take on the value 0, 1, 2, or 3. Okay, so small x will be number of heads in 3 tosses of the coin. It can be 0, 1, 2, or 3. So in this scenario where there's only 3 tosses of the coin or 3 flips of the coin, it is still easy to manually calculate probability of s equals 0, s equals to 1, s equals to 2, or s equals to 3 coins. However, if we have a scenario where we're going to calculate 100 tosses of the coin, or even 1,000 or 10,000 tosses of the coin, then how are we going to calculate the probability of each of the probability outcomes for all the probability in the experiment? Then it will be too tedious. So this is where we need to generalize for the formula or the expression for probability random variable x take on a particular value small x. So we need to generalize. Okay, so that is when this formula or expression for probability x, capital X equals to small x, this expression will be very, very useful. Alright, with this expression, we'll be able to easily calculate probability of x small x number of heads, given that we know the number of tosses of the coin, okay, and probability of obtaining a head in each toss of the coin. Then we can just easily sum in. Okay, so now, and this idea of generalizing the experiment, where the experiment only have 2 outcomes, right? So in this scenario, it is either obtaining a head or not obtaining a head. So this will work only if the experiment has only 2 outcomes for each trial of the experiment. So this idea is the motivation that mathematician or statistician came up with the concept of binomial distribution. Okay, where bi means 2, right? So that's why only 2 outcomes in binomial distribution. Okay,